Hello, my name is Kaylin Ebener, and this is my third lab, a black hole model. In my presentation, I will be discussing how I created my computational model and how I bridged the physics principles to my model. The goals in this lab included relating velocity, net force, and momentum, and understanding and using the breakdown of F-net into its parallel and perpendicular components. Since, according to Newton's law and derivatives, F-net equals dp dt, I will use the relationship dp dt equals dp dt parallel plus dp dt perpendicular in my model and calculations. I will also create a computer model in GlowScript of the orbital motion of a star around a black hole and use the information from the model to calculate the mass of the black hole. The system I will be modeling consists of a black hole of unknown mass located at the origin and a star with a mass of 2 times 10 to the 30th kilograms orbiting it. The position of the star was generated in the starting code based on my email address with a seed. I initialized my GlowScript program with the given mass of the star, the universal gravitational constant, the delta t, which is the time in a day in seconds, and the starting time t equals 0. This model is of circular motion. We know F-net equals the sum of F-net parallel and F-net perpendicular. F-net parallel is equal to dp magnitude dt times p hat, where p hat is the direction of the momentum. P hat is equal to the momentum divided by the direction of the momentum. F-net perpendicular for circular motion is equal to m times the magnitude of the velocity squared over r. From Newton's second law, we know that the net force is equal to the change in momentum over the change in time. If we take the derivative of that, we get dp dt, which describes motion at an instantaneous point in time. With this relationship, we know that dp dt is equal to dp dt parallel plus dp dt perpendicular. We can also see that dp dt parallel describes changes in the magnitude of the speed, while dp dt perpendicular describes changes in the direction of movement. To summarize, F-net describes movement over a change in time, while dp dt describes instantaneous movement with its nature as a derivative. Here's the code I put into GlowScript to account for the net force, as well as its parallel and perpendicular components. dp dt is equal to delta p over delta t. F-net is equal to dp dt, and the code shows this as well. P hat is the unit vector for momentum in the direction of the momentum, and it's coded for by dividing the initial momentum by its magnitude. Shown on the previous slide, dp dt parallel is the magnitude of dp dt times p hat, the direction of the momentum. By Newton's second law, F-net parallel is equal to dp dt parallel, and likewise for F-net perpendicular and dp dt perpendicular. Since in circular motion the parallel and perpendicular components add up to equal dp dt, we can solve for dp dt perpendicular by subtracting dp dt parallel from dp dt, shown in the fifth section of the code. The first section of code calculates the initial and final velocities using an index system, and those velocities are multiplied by the given mass of the star to calculate the initial and final momentums. These values will update with each time step. Next, I calculated the change in velocity and momentum by subtracting the initial values from the final values, respectively. Here is my program running. The model shows the star orbiting the black hole, and the mass data is output in the box at the bottom. You may also notice the arrows stemming from the star that represent the net force is orange, the parallel net force is pink, and the perpendicular net force is blue. The magnitudes of the net force and its components are printed at the very end at the bottom of the box. To calculate the mass of the black hole, I rearranged the universal law of gravitation equation. The mass of the black hole times the mass of the star times g divided by the magnitude of the distance between them squared, and inputted the known values. Here's the code in GlowScript used to solve for these values, and it printed a mass for each time step. The numerical average of all the masses is 1.08 times 10 to the 34th, so that is the mass of the black hole. If this current black hole was removed and one with a different mass was put in its place, but the star's motion data remained the same, we would not be able to tell that there was a swap. This is because the formula used to calculate the mass of the black hole is based on the motion of the star, and the mass of the black hole is not included in the calculation. Thank you for watching.